Hey everybody, tonight I want to prove an inequality for you that has an irrational left-hand side um, and a rational right-hand side. And let's go ahead and note that 17 squared is 289. Yeah, there is a way to do this. I think I'd never tried it, but you can rationalize this, do the usual rationalization. You'd get 1 over 289 underneath this, multiply through, and you'd get an equivalent inequality. You may want to try that. I haven't tried it because I found this lemma that's quite useful. I'm going to go ahead and prove it. You can see the 3 here. We have 3 summands, and you might think this actually comes into play. But let's go ahead and prove this result. You guys probably already know this. This is a fairly straightforward application of the AM-GM inequality. I'm just going to work with the left-hand side here. So we have a squared plus root a plus root a, and there's 3 summands here. All right, and so the AM-GM says the arithmetic mean, which is the sum of the 3 objects divided by 3, is greater than or equal to the cube root of the product. Okay, the cube root of the product. But you'll notice that the cube, well, I'll just write it out. This is a squared times, I'll put the dots there, I don't know if it's necessary now. A square root of a times the square root of a. Live without the dots, I guess. But notice this is just a cubed, and so this is greater than or equal to, this part right here is greater than or equal to just a, right? Or it's equal to a. All right, and you can see that if we multiply through by 3 here, if you take this, multiply it against the a, you get the result here. All right, now you may not, it's fairly interesting how this plays into the solution to this inequality. But again, this is the AM-GM inequality. Notice the 3 here is with respect to addition, summing up 2 things, and then you take the cube root. So this is a fundamental inequality. It's called the AM, Arithmetic Mean, Geometric Mean Inequality, and it's a fundamental relationship between addition and multiplication. Okay, very fundamental. Again, multiply through by 3 right here, and you get the result we're looking for, right? Okay, now let's see how it plays out here. What I'm going to do here is we're just going to repeatedly use it, and we'll use it first for a is equal to 14 over 17, a is equal to 18 over 17, and a is equal to 19 over 17. We just add them up. You can add up inequalities just like you can add up equalities and get another true statement. All right. Now notice the 2 here. This part right here, of course, is just the same thing as 2 times root a, right? So I hope you can see that that's all we did is add these things up 3 times, and you can see exactly where the 3 goes. All right, we just used this object 3 times. All right, now another thing that's fairly handy here is to note that 14 plus 18 plus 19 adds up to 51, right? 32 plus 19 is 51. Okay, that's equal to 51. But notice that 51 over 17 is just 3, right? You see how we go? This is kind of cool here. All right, this part in the parentheses sums up to 3, so we have 3 squared, or you can write it as 14 over 17 plus 18 over 17 plus 19 over 17 quantity squared. You know, it's either way. It's useful to write it this way. You might think, well, why don't we just put 9 here? Well, maybe you can, but this works out nicely with the algebra just to write it going from here to here. So that's kind of a little simple when you see it, but it's not an obvious thing to try, in my opinion. Okay, now we have an algebraic identity here that comes in very, very handy. All right, that basic algebraic identity, I'll just write it out for you, is if you have a plus b plus c quantity squared. All right, that's equal to a squared plus b squared plus c squared. And again, it's kind of tedious. It's just a trinomial squared. And then you have a plus 2 times AB, just all possible 2 variable combinations. 3, choose 2 of them combinatorically. Oh, the T, that should be in front. All right, but let me just, I'll get this straightened out in a minute, folks. So what do we have here? BC and what, AC? All right, y'all, let me get and the 2 comes out front, it distributes, so let's erase that. Get rid of that. And come back here and place the 2 right there. Okay, folks? You see, that's all that happened right here. When you expand this out, you obviously get the square terms, but you get 2 copies of each of these pairs of variables, okay? A, B, B, C. These are called elementary symmetric polynomials, actually. All right. Now, and so that's exactly what happened right here. Okay, that's exactly what, except we just did it we rearranged it to fit the problem. Okay, and again, you can check, these would be like your A, B, B, C, AC things right here. Okay, now when you substitute, when you take this expression and substitute it right here, you can see what happens. It works, it looks kind of messy, but notice we have these 2 objects, okay, that are going to cancel out when you come down to the next line. You see there, folks? That's kind of nice. Those go away. All right, and then so you end up with this expression right here, and see, this is minus. You take it to the other side of the inequality and divide by 2, and you get this. Okay. All right, folks. So kind of nice there. That worked out fairly quickly. Everything kind of dried up fairly fastly. Now let's see here. This would be equal to 14 times 18 plus 14 times 19. And don't worry, I'm not going to try to multiply this out, waste your time. And then plus 18 times 19. And notice they're all over the same common denominator, which is 17 squared, which is 289. Okay. And yeah, you guessed it. These numbers sum up to 860. Okay. So 14 times 18 plus 14 times 19 plus 18 times 19 sums to 860. So we get 860 over 289. And I've always thought these are cool because the irrational numbers are kind of mysterious looking, right? With the rational numbers, you can do a division and get a very, how close they're going to be, how, or what approximately the magnitude of the number. Irrational numbers are a different story. That's why they're called irrational, surds, whatever, the negative, pejorative, So anyway, that proves it, folks. We get this expression is greater than or equal to this. Okay, so right here, this is greater than or equal to this number. Okay, and is that what we're supposed to do? Yep, that's it, 860 over 289. All right, folks, fun problem. Let me know if you have any luck. You can rationalize this, like I said, and bring the 289 out, multiply through, get an equivalent inequality. See what you can do. I don't think it just a direct application of the arithmetic mean, geometric mean gets the job done when you do that. Let me know if you can figure it out more directly. That's the natural thing to do, is to do what they teach you in high school or junior high. Factor this out, it would become 1 over 289 out here. You'd have root 14 times 17, root 18 times, and all that, And then you at least you would just have 860 on the side, and that might be something more tractable. But I tried it. I spent 5 or 10 minutes, and it didn't seem to be working out just by directly applying the AMGM inequality. But anyway, this lemma is very nice here. It's kind of a strange looking thing, but it is true based on the AMGM inequality. AMGM, and this. Again, this is the form for 3 variables right here. Divide by 3, and then when you multiply by the 3, you would get the whole thing is greater than 3a. A squared times the square root of a times the square root of a is a cubed, cubed to cube root of a cubed, and you get a, right? All right, that does it, folks.